This is the last video in the chapter on electronic structure and periodic properties. This is the last periodic property we'll talk about, which is electron affinity. So remember in the last video, we talked about ionization, which was how to make a cation. So electron affinity is about how to make an anion. So the electron affinity is the energy change accompanying the addition of an electron. And these values are measured for a ground state gas atom. The trend is listed here in our mini periodic table. It's a little bit confusing the way I've written it. It increases towards the right and towards the top, just like ionization energy. But when I say it increases, I mean that the value becomes more negative. So if you'd like to think about that as it decreases in this direction, or you can think of it as the number part of it gets bigger. I just like to list it this way because I think it becomes most important for elements towards the right. And you'll see what I mean here in a minute. So it's sort of the opposite of the ionization energy. The electron affinity represents how strongly an atom would prefer to be an anion. Whether it would prefer to gain electrons over its normal neutral state. So when we make an anion with our generic element X, we would have generic atom of gaseous element X. I've already written it wrong, sorry, plus an electron, because we're making it into an anion, and that makes it into a negatively charged gas X. And again, it's the first electron affinity. You could continue to add more and more electrons, and you would have second and third and so on electron affinities. And to help you interpret the number, if you have a large negative number, so like negative 100, for example, this indicates that an anion is favorable. So if the number for your element is really big, then the element really would like to be an anion. If your value is a small negative or positive electron affinity, that means an anion is unfavorable. Particularly if you get a number that's positive, this is really, really unfavorable, really does not want to take on another electron. It has enough. So let's talk about the trends, vertical first, and then horizontal. So as we move down a group, what is happening? Same thing that's been happening for every periodic trend so far. The electrons are moved and they live in orbitals that are further and further from the nucleus as they're added. That means that the Z effective is going to be smaller and smaller the more electrons we add, because they are going to have too many trees in the way. They won't be able to see the positive charge. And that means that it's going to be harder to attract an electron. Because think about what you need to attract a negatively charged electron is a positive nuclear charge. And if the electrons on the outside can't feel much of the positive charge anymore, then electrons probably aren't going to be drawn in if they can't really feel that positive charge. So that means sort of the absolute value of electron affinity, how big the number part is going to decrease down a group. We have smaller negative numbers at the bottom, larger negative numbers at the top. So the largest negative numbers will be in the top portion. And then we'll do horizontal next, moving across a period. So just like we said in the last video, every step to the right we make involves adding one proton to the nucleus and adding one valence electron. And those valence electrons are added to the same shell, so they don't have much of a shielding effect, but adding additional protons increases the effective nuclear charge because we're physically putting more positive charge in the nucleus. And the more positive charge you have in the nucleus, the easier it is to attract an electron to come and hang out in your atom. And if something is easier to do, then the number in the energy is going to be more positive negative number, a larger negative number, sorry. Larger negative number. So it's going to be largest on the right side. So we're going to decreases as we move down, it increases as we move to the right. So fluorine up here in the top corner is going to be the easiest one to make into an anion. And just a note, the same anomalies that we saw in the last video about ionization energy exist here, except that they are all off by one step because we are attracting and adding an electron instead of subtracting. So we discussed that filled, empty, and half-filled subshells are the most favorable. They're the lowest energy orientation for electrons. So if they're in one of these favorable situations, filled, empty, or half-filled, they're going to resist the addition of another electron. They're happy as they are, and they're really going to push back. So for example, if we have our p orbitals and they're totally empty, and we are adding in that first electron and we're ruining the nice emptiness, that's going to be less favorable. So that's going to be a smaller value. We also talked about if we have 2 and we move to 3 in a p subshell, if we're adding the last one, reaching that happy half-filled status, that is going to be favorable. There's going to be a larger affinity for this one. So we're basically going to see the same bumps that we saw in this plot, the same anomalies in the center, but they're going to be shifted over by one atom. So we have finally reached the end of this chapter all about electrons, where they live, how they can be modeled as waves and particles, what kind of orbitals they live in, how that changes the valency and the bonding and the periodic trends based on them. So now we can return to our atoms first approach and we can check off periodic trends. So we are officially finished talking about individual atoms. And from this point on, we will move on to talk about molecules that have multiple atoms in them. Moving up in the world.